Hi there, you're in the lab with me, JJ. Today is Learning the Art of Electronics Day. Today we're going to keep on keeping on through Learning the Art of Electronics. This is, of course, the book that we're working through. It's the Hands-on Labs course from Stanford University. We've already started. We're up to well, we're still working through the notes for chapter 1. Today is not going to be a prac. There's only theory today. I've managed to make some more notes, and we'll be revising everything that we've done so far. It looks like, apart from today, next week will be a little bit more theory as well. Although maybe we could do a prac. We'll see. But no prac today, maybe a prac next week. We're almost through the notes for chapter 1. And once that's done, we'll be up to the lab, which is really the meat of the course. So, what we're going to do is we're going to go over to the computer, and I'm just going to run you through the notes that I've made from the book so far. And that's all that we'll be doing today. It's just revision of the notes from chapter 1. And next week we'll continue. We're almost through the whole chapter, so that's good. Anyway, let's jump over to the computer and have a look at what we got.
All right. Well, here we are on the computer. So I'm just going to fire up the old web browser here, make sure you can see it. And I've got some stuff here. Might as well show you from the top. The show's wiki is the ITL wiki. It's on the web at inthelabwithjj.com/wiki. We'll be looking at our Learning the Art of Electronics project. This is all public access content that I'm showing you at the moment, but we will be going through to the notes, which are restricted access, subscriber only. But you don't need it. You can just follow along with the videos as we're doing now. So as you can see, we've been working through chapter 1N, DC circuits. Today we're up to page 22, and we're looking at figure 1N33, which we'll get to in a moment. So let's open this up. And I've actually started moving the various chapters into their own page, just because otherwise the content was too large. So as you can see, this document is a work in progress. It's not complete yet. We will complete it and we'll move on with the rest. And you can also see this is subscriber only material. So if you want access to these notes, you are very welcome. And you if you support me on Patreon, I'll set you up with an account. So we're just going to be going through from the top. So we've seen a lot of this before, of course, and so it's just revision. But revision, it's good to do revision. So I'm just going to skim over the notes with you. I'll call out the stuff that's in green because that's the main notes. So what we're really interested in this first chapter is how to make a voltage divider. Voltage divider is a central idea in this chapter, and it's what we're learning about. The subject of the course is the rules, the laws, rules of thumb, and tricks that constitute the art of electronics. So when delivering power to something, that something is called a load. This course is concerned with electronics to model and process information. So delivering power to something's not really our bag. Certainly a very important thing to do, but this course is about information. And it asks the question here, is it better to model information with voltage or current? And the answer is that a voltage is better, because with current you actually have to consume power, but with voltage you don't have to consume power, or much less of it anyway. Everyone should know Ohm's law, V equals IR, or as my friend Ali the Dazzling says, I equals V divided by R. He thinks it's important to isolate the output, which is the current, from the inputs, which are the voltage and the resistance. It's an interesting take. Actually, let's take a quick break, and I'll make that note here in the notes. Just give me 1 second. All right, I'm back now. If we just hit F5, refresh. There we go. So I've got a note here. Ali the Dazzling prefers I equals V divided by R, which is just another way to organize the variables in this equation. The reason he prefers it is he says the current is the effect and the voltage and the resistance are the cause. So he likes to think of effects and causes. So fair enough. And we've got a note there now. Check out the video if you're interested. Just click through. It's on YouTube. All right. And as they said, the glib Stanford student will say, a volt is what pushes an amp through an ohm. A volt will push an amp through an ohm. All right. Another way to say the same thing is that 1 volt is the work done as one adds 1 joule of potential energy to 1 coulomb of charge. Ohm's law is useful, but it only applies to resistors. Not everything is a resistor, of course. The inverse of resistance is conductance, and conductance is measured in Siemens, and it's expressed with G equals 1 on R. So the reciprocal of the resistance is the conductance called G, which is in Siemens, which is S. So you will see that. In most metal conductors, conductivity degrades, increasing resistance when temperature increases. So the basic idea is that all of and when it gets hot, it gets highly kinetic, and the bumping around degrades the conductivity. Doesn't always work this way, but it usually does. We've got a mathematical expression here that relates energy to the voltage and the distance between the points of interest. I don't think we care much about that in this course. We'll see, I suppose. There are various strategies for making a resistor: carbon composition, carbon film, metal film, and wire wound. But it's important to remember that many electronic components do not obey Ohm's law, as we shall soon see. So don't expect to use Ohm's law where it doesn't fit. It only works for resistors. We can extend the reach of Ohm's law with dynamic resistance, and that's where the dynamic resistance equals the change in voltage divided by the change in current. So there's this, there are these graphs here which show various resistances. So we've got a straight up resistor that's sort of just linear, it's a line. A lamp, the resistance changes with temperature. A diode looks something like this. A current source just goes straight up to infinity. You'll never find a perfectly ideal current source, but that's basically the idea of one. Now these curves have been plotted with V on the y-axis and current, so V for voltage on the y-axis and I for current on the x-axis, and the reason for that is so that this tangent here will come out in ohms. If you flip the axes, the tangent would come out in Siemens, which is conductance. So usually you see them the other way around, but they've been set up this way for this picture, just so that this number here is in ohms. So power is the rate of doing work, and components will have power ratings. So they need to dissipate the power, usually as heat or light or mechanical work or whatever it is. So it's important to make sure you don't exceed the power ratings of your components. The resistors that we work with are typically rated at 1/4 watt. In fact, the ones that I got for this, which are up there behind me, they're 1 watt. I got 1 watt resistors for our experiments, which is overkill. They only needed to be 1/4 watt. Anyway, they're nice big chunky things that you can read the color bands on. So the formula for power is just current times voltage. And if you combine that with Ohm's law, you can get different expressions for power. You can get I squared R or V squared on R. To find the minimum resistance for a 1/4 watt resistor at 15 volts, you just throw in 1/4 watt equals 15 squared divided by R min, and then solve for R min, and you get 900 ohms, which is pretty close to 1 kilo ohm, which is the minimum safe value at 15 volts. And as current measures charge per unit time and voltage measures work per unit charge, the charges cancel and you get power is work over time. This is power. Okay. In this course, we rarely worry about power, so we're not super interested in power, except when we have to power things. So there's a bunch of references in here: Art of Electronics, Principles of Electronic Circuits, and the E&M, Electricity and Magnetism course. So if you've got those books and you're following along, this is material you should try to cover if you've got some time. Now this is Kirchhoff's laws, Kirchhoff's voltage law, and Kirchhoff's current law. Now I'm sorry if I'm saying Kirchhoff wrong. I'm not 100% sure how to pronounce it. And this had me well and truly stymied. If you've been following the channel, you will know that I recently took some time to make some battery holders with power clips attached so that I could model this, which I completely misunderstood. I thought that they were saying that if you had power source, like if all of these A, B, C, D, and E were batteries with a positive terminal and a negative terminal, when you added them all together like this, it'd just be a massive short circuit. So I didn't understand what it was getting at. But thanks to ChatGPT, who explained it to me, these aren't all supposed to be considered as power sources or batteries. They're just components in a circuit. So this could be a voltage source, and this and this and this and this could be resistors. And then if this was the power source and these were all resistors, when you start here, you would start at the maximum voltage and you would lose a little bit of voltage across each of the components. And when you got back down here, it'd be zero. So that's what that means. If you can follow the curve around, then by the time you get back to here, all of the voltages have completely dropped to the lowest value, which we call zero. So I'm glad we got that little bit of confusion out of the way. These are not all power sources. They're more likely to be resistive or whatever. And the current Kirchhoff's current law regards what they call algebraic current, which means that the sign of the current actually matters. If it's positive, it'll be flowing in. If it's negative, it'll be flowing out. So the currents in and the currents out will be zero. So, but that's of course the algebraic sum. So we can say that the total current is the same everywhere. The parallel current is the current through 1 and the current through 2 added together. The series voltage is additive, so the voltage 1 and voltage 2, and the parallel voltage is just the same everywhere, V1 and V2. So we've got applications of Kirchhoff's laws, series and parallel circuits, a couple of truisms probably familiar to you already. So there's a voltage drop here and a voltage drop here, and the current's the same all the way through. And here, this voltage and this voltage are the same, but the current through here and the current through here is split. And then they do make the point that this is actually a circuit. You need to know that this part here comes back to here and joins up at the power supply as shown here. So this doesn't look like a circuit, but it is, because this is the circuit that it indicates. And they make the note here that with parallel resistances, it's the conductances that add. So the resistances don't add, but the conductances do. Which is how you end up with this. The total conductance is the conductance 1 plus the conductance 2, and as the conductance is the reciprocal of R, you get 1 on R1 plus 1 on R2, and you can solve this system for two resistors with R1 times R2 divided by R1 plus R2. That only works for two resistors. If you have three resistors, it gets bigger. So here are some easy cases. You've got R here and R here, then you've got half R. And if you've got R here and 10 here, then you've got 1/11 of R. And if you've got R and 2R, then you've got, I think, 2/3 of R, is it? Yeah, 2/3 of R. Oh, what did I say before? Here, this is, yeah, 0.91 R. And this is 2/3 of R. All right. And if you've got them in parallel, it's the small resistance that dominates. And if you've got them in series, it's the large value which dominates. So that's a handy rule of thumb. Oh, this is our first rule of thumb. So in a parallel circuit, hang on a sec. I've got a sneeze coming, but it won't come. It's so annoying. All right, this is our first rule of thumb. So in a parallel circuit, a resistor much smaller than the other dominates, and in a series circuit, the larger resistor dominates. All right, so now we're working our way up to actually making a voltage divider. Oh, there's a note here, because we'll be using potentiometers, which is a 3-terminal device that meters out potential. A variable resistor is a 2-terminal device, and you can get one by using only 2 of the 3 terminals from a potentiometer. But when you do that, when using a pot as a variable resistor, it's a good idea to tie one end to the wiper. This means that if the wiper comes loose, the maximum resistance is seen instead of an open circuit. This can be important as you probably haven't tested your circuit with an open circuit resistance from this component. So as the terminals get old and age, they can come loose. And if you tie off one end, you'll get the maximum resistance rather than an open circuit when that happens, which is probably going to be better for your circuit. And here we go. This is a voltage divider. So we've got 30 volts in. We've got a 10K resistor here and a 10K resistor here, which means that there's 15 volts on the output. And the currents are the same through the whole network. Okay, so three ways to analyze this circuit, and the first way they do it is to use Ohm's law. So we calculate the current as Vin divided by R1 plus R2. So we get a value for the current, and then once we know that, we can plug it into here to say that the output is I times R2 over here, and then that's 15 volts. So, and they say, but this method takes too long. So the second method is to rely on the fact that I is the same in top and bottom. Once you know that, you can muddle through and express the voltages in terms of resistances and currents. And then we get this equation 1n.1, where the output voltage equals the input voltage times R2 divided by R1 plus R2. And you can plug in the numbers for this case. It says here that you'll use formula 1n1 fairly often. So I really need to do something to make this. I'll put a box around it and call it formula 1n1 or something. It's not highlighted enough for me. Actually, give me a sec. I'll do that now. All right. So I fixed that up. I'll just click here. And if I just reload the page, okay, I've put a box around it and labeled it formula 1n1. So There we go. So it says here you will use formula 1M1 fairly often. So to calculate the output voltage, it's the input voltage times R2 divided by R1 plus R2. Okay, and then the third method of solving the voltage divider is just to muddle through with explaining it to yourself, and you can say, since the currents in top and bottom are equal, the voltage drops are proportional to the resistances. Later, impedances, a more general notion that covers devices other than resistors. So in this case, where the lower resistance makes up half the resistance, it will also show half the total voltage. As another example, if R2 is 10 times R1, then it will show 10 out of 11 of the input voltage, roughly 91%. Loading and output impedance. So next we need to think about what happens if someone comes and attaches a load to our voltage divider. And the tedious method of solving this is to model the bottom as a voltage divider, and calculate a new V out. Treating these as parallel, they're effectively 5K, and then you can say you've got 30 volts here, you've got 10 here, 5 here. This will be 20 volts. And as they say, this is the tedious method. So there's a better way, and that's using Thevenin's model. And here's how to calculate the two elements of the Thevenin model, the Thevenin voltage and the Thevenin resistance. So you note that load is not part of the Thevenin model, so you just ignore the load for the Thevenin model. And the Thevenin resistance is R1 in parallel with R2. So the process is basically to take any independent power sources and short them. And if you do that, then R1 and R2 are in parallel, which is the justification for this expression here. So the Thevenin voltage is easy. It's just the open circuit voltage. And the resistance also pretty easy. It's just in parallel. So this was Thevenin's good idea. Model the actual circuit unloaded with a simpler circuit, the Thevenin model, which is an idealized voltage source in series with a resistor. One can then see pretty readily how that simpler circuit will behave under various loads. So Thevenin voltage is just the open circuit voltage, and then the Thevenin resistance is formulated as the quotient of the Thevenin voltage divided by the short circuit voltage current, which is the current that flows to ground if you simply short the output to ground, which you don't do because doing so is dangerous. So the shortcut calculation of the Thevenin resistance, given a circuit diagram, the fastest way to calculate the Thevenin resistance is to see it as the parallel resistance of the several resistances viewed from the output. So this is the output, and when you look back into the circuit, you see these two resistances are in parallel, which allows you to calculate the Thevenin resistance here. The Thevenin voltage is just the input. It's our formula 1N1 again, which we saw earlier. So the Thevenin voltage is just the voltage that results from the voltage divider here. So there's some references there to Art of Electronics. Now, I'm going to read this all out, but honestly, I'm not sure. I don't find it to be particularly clear. But what they're trying to do is justify the Thevenin shortcut, and this is what they say. The shortcut shown in Fig-1N.33, which is this and this, asserts that the Thevenin resistance equals the parallel resistance of these resistors. But this result may strike you as a little odd. Why should R1 going up to the positive supply be treated as parallel to R2? And then it says, well, suppose the positive supply was set at 0 volts. Okay. Then surely the two resistances would be parallel. right? I don't know that that necessarily follows. Or try another thought experiment. Redefine the positive supply as 0 volts. It follows then that the voltage we had been calling ground or 0 volts is now negative 30 volts, to use the numbers from figure 1N.33. In this case, it seems clear that the upper resistor to ground matters. The lower resistor, going down to 30 volts, is now the one that seems odd. But the circuit doesn't know or care how we have chosen to define our 0 volts or ground. I don't see how definitions for the voltage at ground bears on these points being shorted to each other. Anyway, the point of playing with the definition of ground is just that the voltages at the far end of those resistors seen from the output do not matter. It matters only that those voltages are fixed. Note, later we will relax this requirement too. Thevenin's model works as well to define the output resistance of a time-varying voltage source as it does for a DC source. Or suppose let's take a different divider, designed to make the numbers come out nice, with Vin of 20 volts divided by two 10K resistors. To discover the impedance at the output, do the usual experiment. A general definition and procedure for determining impedance at a point is to discover the impedance at a point, apply a change in voltage and measure a change in current. And the quotient is the impedance. The figure 1N.23 uses the small signal or dynamic version of Ohm's law. In this case, 1 milliamp was flowing before the wiggle. After we forced the output up by 1 volt, the current in top and bottom resistors no longer match. Upstairs 0.9 milliamps, downstairs 1.1 milliamps. The difference comes from U, the wiggler. So happily 5K is the parallel resistance of the two R's. So we did do this experiment together, and we did get those numbers. You apply this. We added an extra volt here, and then we measured the current. Rationalizing Thevenin's result, parallel R's. Any non-ideal voltage source droops when loaded. How much it droops depends on its output impedance. The Thevenin equivalent model, with its Thevenin resistance, describes this property neatly in a single number. So the output impedance and the Thevenin resistance, for our purposes at the moment, are the same thing. And there it is there. And I asked ChatGPT, I said, are output impedance and Thevenin resistance the same thing? And it says the short answer is yes. In practice, they're the same concept. And then it goes through a bunch of mathematics, and it comes up with the one-line takeaway. The output impedance equals the Thevenin impedance. If you're only dealing with DC and resistive cases, the Thevenin resistance is the same as the output impedance. And then I asked ChatGPT to please explain the Thevenin model to me, particularly why we can treat the various resistances parallel to each other. So this is what I wasn't satisfied about from the textbook. I didn't think it explained that particularly well, but this is what ChatGPT had to say. So Thevenin's theorem, quick, intuitive, plus mathematical explanation. Actually, before we continue, I'm just going to get a fresh coffee. I'll be back. Well, I didn't make coffee. I just had an orange juice. So we're ready to have a look at this explanation from ChatGPT about Thevenin's theorem. The short version, any linear circuit seen from two terminals can be replaced by a single ideal voltage source, the open circuit voltage, the Thevenin voltage, in series with a single resistance, the Thevenin resistance. You get the Thevenin voltage by finding the open circuit voltage between the terminals, and you get Thevenin resistance by turning off independent sources and finding the equivalent resistances seen into the terminals. Your specific question, why can several resistances be treated as parallel, is answered by the same idea that defines parallel resistors. Two or more resistors are parallel when their ends are connected to the same two nodes. So the voltage across each resistor is the same and their currents add. When you compute the Thevenin resistance by turning off sources, many resistors in the original network end up connected between the same two terminal nodes, so they are mathematically parallel. Below I show this both intuitively and with algebra. How the Thevenin procedure makes things parallel intuitively. 1. Remove the load and look into the circuit from the two open terminals, call them A and B. Turn off all independent sources. Replace ideal voltage sources with a short circuit. So 0 volts is a wire, and replace ideal current sources with open circuits. 0 amps is a break in the wire. 3. After those replacements, the circuit often simplifies. Several resistor branches that used to be connected through sources or other parts may now have both of their ends connected directly to the same two nodes, A and B. Whenever that happens, those resistor branches are now simply multiple resistors between node A and B. That is, they're parallel. 4. Combine those parallel resistors with the parallel resistor formula to get the single equivalent Thevenin resistance. So it's not magic, it's the topology after deactivating sources makes multiple resistors share the same two nodes, and sharing the same two nodes is exactly the condition for being in parallel. So this talk of topology, that makes more sense to me than talking about which voltage is defined to be ground. And also, this just says that that there is actually a process of replacing the voltage sources with a direct short. Anyway, so we've got a simple algebraic proof with two resistors in parallel. Suppose after turning off sources, you have two resistors R1 and R2, both connected between terminal A and terminal B. Put a test voltage V test across AB. The currents through each resistor are given as I1 equals V test on R1 and I2 equals V test on R2. The total current drawn from the test source is I1 plus I2, which can be re-expressed in terms of voltages and resistances. The equivalent resistance seen by the test source is V test divided by current total equals 1 over 1 on R1 plus 1 on R2. That is the standard parallel formula. The same derivation generalizes to NN resistors between the same nodes. Right, so this is just how you do it with more than two. That algebra is the fundamental reason we can replace multiple resistors attached between the same two nodes by a single parallel equivalent. Well, there we go. Well, that's a much better explanation, isn't it? An illustrative example, why nodes collapse to make parallels. Imagine a circuit with two resistors RA and RB, each connected from a node to an independent voltage source, and those sources happen to be shorted when deactivated. After you short the voltage sources, the previously separate nodes become the same node, and RA and RB now share the same two terminal nodes, so they become parallel. This is why we always do the turn off sources step before computing the Thevenin resistance. If there are dependent sources in the network, you cannot simply short or open them. Talking about dependent sources now. You must instead apply a test source at the terminals and compute the Thevenin resistance as the test voltage divided by the test current. but the same parallel reasoning applies. Once you look in from the terminals with the proper method, any branches that connect the same two nodes are parallel. A quick checklist to know when resistors are parallel. Are both resistor ends connected to the same two nodes with no intervening element between them? Then they're in parallel. Do they share the same voltage across them? Then they're in parallel. Okay. If turning off independent sources causes different nodes to become the same node, e.g. a voltage source shorted, then previously non-parallel branches may become parallel. Short summary. Thevenin reduces a network to Thevenin voltage in series with Thevenin resistance. To find the Thevenin resistance, turn off independent sources and look into the terminals. Any resistors that now connect the same two nodes are parallel because they each have the same voltage across them. Their currents add, so their conductances add. Algebraically, currents add, so 1 on R equals Req is the sum of 1 on Ri. Req, I think it just means RTH. And then I ask it, please tell me what is a linear circuit and what are other types of circuit. So this is me just asking questions of ChatGPT. Because they talk about a linear circuit, I didn't really know what that was. So ChatGPT explained it like this. What is a linear circuit? A linear circuit is one whose input-output relationships satisfy the two properties of linearity. One is homogeneity or scaling. If you scale the input by a constant, the output scales by the same constant. If input xt produces output yt, then axt produces ayt. Additivity or superposition. The response to a sum of inputs is the sum of responses. So if x1t implies, is it, or changes or goes to y1t, and x2t goes to y2t, then x1t plus x2t goes to y1t plus y2t. I still don't get I don't get superposition. Yeah, I've heard of it, particularly in quantum mechanics. And it's got something to do with additivity, but I don't completely get it yet. Hopefully I do eventually get it. It hasn't clicked for me yet though. And they talk about a system F, and I don't know why they call it a system. Is it? And they use square brackets rather than parentheses. So, is it? I don't know why they don't just use normal brackets here. I don't know. Anyway, let's just muddle through this. Certainly have a look at it if you're interested. It talks about the different types of circuits that are not linear circuits, and there's a whole bunch of them. And I also asked about dependent sources, because when you're computing the Thevenin resistance, you only remove independent sources. But if you've got a dependent source, you've got to treat it differently. And there's 4 different types of dependent sources. A voltage-controlled voltage source, a voltage-controlled current source, a current-controlled current source, and a current-controlled voltage source. And they've all got different ways of being expressed in SPICE, which are noted here. This is extra material. The coursework didn't go into this detail, but I had a bit of a look at it. We won't go through it in great detail here. If you're interested, by all means, check it out. It's in the notes here. And then we're up to the point where we can apply the Thevenin model. So suppose that we try to measure V out at the output of each divider. If we measured with a perfect voltmeter, the answer in all cases would be 10 volts. And then it asks about the significant digits that it's valid to. And they say it could be 10.0 volts, but it could be a bit less than 9.9 volts or a bit more than 10.1 volts. If the 20 volt source were good to 1% and we use 1% resistors, we should not expect perfection. Cool. Now this is what we did in our experiments. We did the small resistances here for the analog meter, and we do the large ones with the digital voltmeter. So we will actually see the RN of our voltmeter loading the circuits, and we did that. So this was our experiments with the VOM, the volt ohm milliammeter, and you can see here that the 9.95 is pretty good. 9.76 is also pretty good. 8.05 is showing obvious loading. So when we were measuring 100K network, then the voltmeter affected the readings. So so when the meter shows us 8 parts in 10 across the dividers, the Thevenin resistance, called the output resistance, we must be dropping the other 2 parts in 10. The relative sizes of the 2 resistances are in proportion to these 2 voltage drops. 8 to 2, which is 4 to 1, which means that the input resistance of the VOM is 4 times the Thevenin resistance, which is 200K. And you should be able to find on your VOM a specification such as 20,000 ohms per volt. And we did indeed find that on our voltmeter. So the VOM specification of 20 ohm per volt describes the sensitivity of the meter movement, which is the guts of the instrument. And then we tried the experiment again with higher numbers for the DVM, and we got these values again: 100K and 1 meg, no problem. 10 meg, obvious loading again. Talking ourselves to an answer, the Thevenin resistance is 5 megs. We're dropping 6.69 volts out of 10 volts across the input resistance of the DVM is approximately 2/3, and 10 volts minus 6.69 volts is 3.31 volts across RThev, approximately 1/3. So the input resistance of the DVM must be 2 times RThev, which is 10 meg. And indeed, we calculated all these values as well. And the multimeter I was using was the EEV blog BM2257 multimeter, and I looked it up on page 19 of the user manual. Is the impedance while in DC voltage mode, which is 10 mega ohms, which agrees with our calculations. So there you go. I asked ChatGPT just straight up because I had trouble kind of getting it right in my head. I said, if the output impedance measures how stiff or droopy an output is a higher output impedance more droopy or more stiff? And the answer is more droopy. So higher output impedance equals less stiff. The output voltage sags more under load. So you really want a small output impedance and you want a large input impedance. And particularly field effect transistors, the FETs are really good at that apparently, which is why we have CMOS computer chips that kick ass because of the input impedance of the field effect transistors. We'll probably get to that in this course. We haven't covered it yet. And ChatGPT gave me a bunch of mathematics. I didn't look at it closely. I did obviously convert it all into LaTeX so that it's properly formatted. If you find any errors or omissions or anything, well, please let me know and I'll fix it up. Okay, so, and I asked ChatGPT to please explain a meter movement to me. And it said, I said, here movement is a noun, not a verb. It's not talking about something that's moving. It's talking about the bit that moves. It's a noun. I'm not sure why it gave me all this maths. I didn't read this closely. There you go. So VOM versus DVM, a conclusion. So a DVM is a better voltmeter, at least in its RN. As a current meter, the DVM fares no better than the VOM. So there you go. The question for ChatGPT was, is it generally better to have low output impedance and high input impedance? And the answer is yes. For voltage mode signals, you usually want a low output impedance and a high input impedance. There you go. Now, there was a digression on ground. So the concept of ground, also known as earth, can mean different things. There's local ground. This is what we care about. It's a common point in our circuit that we arbitrarily call 0 volts. Only rarely do we care if this point is connected to earth ground. All points labeled local ground are electrically connected to each other. And earth ground, these are wires connected to a metal pole that has been driven into the ground of planet Earth. Sometimes local ground is connected to earth ground, such as the ground clip on a scope probe. When local ground is connected to earth ground, you need to be careful not to attach supply voltage. Here is a picture of an earth ground. So there's a picture here, and this is from good old Australia. So this is just the ground attached to a steel peg that's been driven into the ground. I don't know if it's steel, some sort of metal. And then there's signal ground. So I drew these out. Local ground looks like this, earth ground looks like this, signal ground looks like this, but people use them differently, so you can't, sometimes, but not always, local ground, earth ground, or signal ground are connected to each other. There are schematic symbols to represent local earth and signal ground, but they are not used consistently. Sometimes chassis ground is connected to local ground, and sometimes to earth ground, and sometimes to both. So chassis ground, you really need to know what they're talking about, because it could be local ground, could be earth ground, could be both. So here we are developing our next rule of thumb, which is a rule for relating the output resistance of A to the input resistance of B. Voltage dividers whose outputs we tried to measure introduced us to a problem we'll see time and again. Some circuit tries to drive a load. To some extent, the load changes the output. We need to be able to predict and control this change. To do that, we need to be able to understand the characteristic we call Rn and the characteristic we call Thevenin resistance. In future, when we meet frequency-dependent circuits, we will generalize both characteristics to input impedance and output impedance. Design goal. When circuit A drives circuit B, arrange things so that B loads A lightly enough to cause only insignificant attenuation of the signal. There's a typo here. I'll fix that and I'll come back. All right, I'm back now. I think we were missing a 2. Let's just hit refresh. There he is. Lightly enough to cause only insignificant attenuation of the signal. This design goal leads us to our rule of thumb. Design rule of thumb: when circuit A drives circuit B, let the output resistance of A be less than or equal to 1/10 the input resistance of B. This problem is a voltage divider. When R out A is a small fraction of R in B, then the voltage divider delivers most of the original signal. When the relation is 1 to 10, as we propose, then the voltage divider delivers 10 out of 11 of the signal, and attenuation is just under 10%, which is good enough for our purposes. So we've got a design rule of thumb: when circuit A drives circuit B, let R out for A be less than 1/10 of R in for B. So that's our rule of thumb, and this is how those circuits couple to each other. And there's 2 ways of looking at that over here. So, and then if the big signals, and this is actually where we get up to today, but looking ahead just a little bit, If signals were our only concern, we could just amplify our inputs. So it's not the size of the signals really. The reason we have our rule of thumb above is that it lets us design sub-circuits independently. This means we don't need to consider A and B as a single large circuit, which makes our design work more manageable. And now they've got a question here. What is the Thevenin resistance for less than 10% droop? And what are these R's? So what resistance here and here to drive this circuit here where we've got 10K in top and 10K in bottom? I don't really know the answer to this yet because I'm not sure if the input resistance of B is these in series. It could be these in series, so it's 10K plus 10K. Is that the input that we need? So it's 20K, and we want to be less than 1/10. So this could be 2K and 2K. I'm not sure. I don't know how to think clearly about this. I would appreciate some worked examples, so I could try and grok how it all gets done. But I haven't got this figured out yet. But I will have a think about it before next week, which will get to the end of this chapter. So there will be one more session for this chapter, and that'll be coming out next week. Also, I've got the notes here for the reading in the Art of Electronics, which is of course the textbook that goes with the course, and they've referred us to some sections in chapter 1: the introduction, the section on voltage, current, and resistance, and a section on signals. It also referred us to the Appendix C for resistor types and Appendix H for the transmission lines and impedance matching. So I guess in the next week I'll try and get some of these written up as well. Although honestly, I kind of have my hands full just writing up the notes for this book. It's for the Learning the Art of Electronics. So this extra stuff I may or may not get around to, but we'll see how we go. So that concludes today's notes, which has obviously been mostly revision, except for this little bit in the end here. So there will be one more next week. But I guess I'll take you over to the farewell cam and we'll wrap up.
That's a wrap. So just keeping on with the Learning the Art of Electronics. We're almost through the first chapter. We'll finish that next week. I've got all sorts of notes to write up. So hopefully I can find some time to do that. But that is the end of this video. So I hope you enjoyed this video. Thanks very much for watching, and please remember to hit like and subscribe.